So let's take a look at the threats to the power system. Not an exhaustive list necessarily, but it was a number of things I could quickly think of. Wind and ice, trees, flooding, animals, squirrels and such, getting into places they shouldn't, shorting things out. Car strikes, cars hitting poles, substations, things like that actually happens a fair amount. Misoperation of equipment, either settings are wrong or it was operated incorrectly, causing problems. Lightning strikes, attacks, either physical attack, like shooting up a substation, like in California, right, or cyber attacks. And we'll hear about some of those cases, like the Ukraine cyber attack. We'll hear in a little bit. And then earthquakes and tsunamis. So we are going to obviously in this course, the Cascadia Subduction Zone is in the title of the course, right? So obviously we're going to be focused on the earthquake and tsunami part. I have a lot of focus on that. But some of the metrics and framework that we're going to talk about, particularly in the second half of the day, have applicability to almost any of these things, right? Quantifying sort of the risk or the probabilities of different things happening. Right? So we're going to focus on this, but hopefully some of the things that we talk about will have applicability to any area of resilience or reliability. Okay. So let's talk about a little bit of our situation. So the ring of fire. So of course we're right here, right? And then we have Japan. So we're going to talk about a couple different historical cases. Japan, New Zealand, and Chile. Which you can notice that those are all on that ring of fire. So what's happening there is we have the Pacific plate pushing out and subducting under the continental land masses and producing all that volcanic activity in those earthquakes. Right? So these countries, so when we look at what's happening in other countries, right, places like Japan, New Zealand, or Chile should be very interesting to us because they're sort of geological mirrors. They're looking at a similar situation to what we are. Here's just another slide showing that. So, and one other thing I'll mention is that a lot of this material in the Cascadia Subduction Zone part, this first part of the presentation, a lot of it is from the Oregon Resilience Plan. Does everyone know about that document? If you don't, so the reference is right here, and I also have a list of references at the end of the presentation, or at the end of all the slides, at the very end of all the slides for the course, and also put up on the course repository so you can get it there. But if you're looking for just a kind of a rough introduction, it's a little outdated now. It's about 5 years old. It was done in 2013. But if you're interested, it's an excellent thing to follow up with. And I'll show you that reference later. But a lot of this information is from that. But anyway, the Pacific plate pushing out and subducting under the North American plate and the Eurasian plate, or the Okhotsk plate on the Japanese side, and producing that fault activity. So if we look at here's Japan and here's us, so we're very much a mirror situation. So we have this plate subducting under the North American plate, and for Japan, the Pacific plate subducting under the Okhotsk plate, and that produced, then you have this subduction fault. And so that's a mirror. For us, we have, you'll notice we have, now we call the Juan de Fuca plate. So I said the Pacific plate before, but the Pacific plate actually connects to the Juan de Fuca plate here. And the Juan de Fuca plate is actually technically what is subducting under the North American plate. But I just want to point out a couple things in the slide. You'll notice that right here, see these arrows going other directions. There's actually material upwelling there. So material coming deep within the earth and upwelling and then spreading those plates. So that's a spreading fault right there. And that spreading fault is pushing that Juan de Fuca plate against the North American plate. One other thing I'll point out is that there's at least a couple different kinds of faults that are shown here. You notice here, this plate right here, this fault right here, you'll notice that if that's spreading, this interface is grinding against each other this way in parallel. And so that's one particular kind of fault. And then here, where that plate is subducting under, is a different kind of fault. So different kind of faults produce different types of seismic activity. But we'll focus on the subduction fault. So you have the Juan de Fuca plate diving under the North American plate. And so what happens in our particular case is that's stuck. So the Juan de Fuca plate is pushing the North American plate back. It's spring loading it. It moves a couple inches per year. And pushing that back and spring loading, of course, eventually what's going to happen is it's going to pop. It'll pop and release all that energy that's stored up. So it's only a couple inches per year, but you can imagine with that much mass and that much length of fault, several hundred miles, there's a tremendous amount of energy there. When does this happen? When did it happen last? So the last one I figure was about 300 years ago, about 1700 approximately thereof. Know this from a couple of different factors, mostly archaeological information. So for example, here's a cutaway where you see here's some fire pits. from Native Americans and Native peoples. And then there's a layer of tsunami sand and tidal mud on top of that. And so the earthquake happened and deposited all that new material on top. It's also known from, there's forests, there's forested areas along the Oregon coast you have these buried petrified forests that had been above land and then they're suddenly underwater. And so that also then you had an earthquake and the subsidence of the land shot out and down and became covered with water. So evidence like that tells us that has happened. But when you look at that archaeological information, how frequent is that? So it happened 300 years ago, but how much was it before that? Right? The timeline looks something like this. So we are here, and this is 10,000 years ago. It's 8,000 BC. Right? So we're living in this little lull right there between the black arrow and that big red line. That big red line was that last magnitude 9 earthquake, which is about 1700. Right? And so we can see here that obviously this is not a rare occurrence. Right? We happen to be living in the little lull right here, but it's not rare. Okay? So the thicker lines are 9 plus, and the thinner lines are 8 plus. And I'll talk a little bit about what that 9 and 8 means. But anyway, if we do a statistical analysis of this and see, well, how frequently does that occur? We have something like about a 10% chance of a great earthquake, something approaching a magnitude 9 in the next 50 years. And something like a 30 to 40% chance for an 8 plus in the next 50 years. So there's a chance that we might live out our life and not see it happen. But it's a fairly good chance that something's going to happen, right? And certainly it will happen eventually. Right? Obviously, this little window is not going to go on indefinitely when you look at this history. Yeah. So it's something that it's part of our area. It's part of our history. So when you talk about that magnitude, what do we mean by that? So the magnitude scale is a logarithmic scale. So each number is a factor of 10. So the difference between 6 and 7 is a factor of 10 greater, and the difference between 7 and 8 is a factor of 10 greater. Well, 10 greater what? It's the amplitude of shaking. So the difference between a 7 and 8 is 10 times greater ground movement than an 8 and a 9 and a 10. Each of those factors is 10 times greater ground movement. Well, now the amount of energy that's released in the earthquake is proportional to the amount of ground shaking to the 3/2 power. So the difference between a 7 and an 8 in terms of energy is 10 to the 3/2, which is about 31.6. So the difference between a 7 and an 8 earthquake is 31.6 times as much energy. And the difference between an 8 and a 9 is 31.6 times as much energy. The difference between 7 and 9, 2 orders of magnitude, is 31.6 squared, which is 1,000. So the difference between a 7 and a 9 is 1,000 times. And that's shown in the size of these circles here. The size of the circles are proportional to the amount of energy that's released. Right? Just give you a sense that the difference between 7 and 8 is not like one more, it's a lot more. And the difference between 8 and 9 is a lot more. It's a logarithmic scale. But the scale, so what scale is it? A lot of people have heard of the Richter scale. The Richter scale is no longer a favored scale. It's still used in some areas of California, but it's fairly outdated. And it originally was only intended for a certain type of earthquake, relatively shallow crustal earthquakes. Right? But it also is a logarithmic scale. However, what's now favored is something just called the magnitude scale. So anytime I talk about something being a 7 or 8, I'm talking about that magnitude scale. It's an extension, just so you know the history of it, it's an extension of the Richter scale that was for deep and distant earthquakes, more appropriate for something like a Cascadia Subduction Zone. But it's also a logarithmic scale. So everything I just said, so 7 and 8, 8 to 9, is 10 times as much ground motion, 31.6 times as much energy. Right? So that's the magnitude scale. That's the major one that we'll talk about. However, there's another one that we'll talk about called the Modified Mercalli Intensity Scale, or MMI. And that's an entirely qualitative scale. So there, when we say like a magnitude 5, it doesn't refer to a particular amount of shaking. Well, I mean, it does, but in a qualitative sense. It's what people would feel. So let's give an example of that. So this is all in MMI, and then we'll talk about that. This is the 2011 Tohoku earthquake in Japan, which is one of their major case studies. Because as we mentioned, Japan is an excellent geological mirror for Oregon. And so we notice these red, so bright red and yellow, and then kind of a bluish green. And then this is what's simulated or expected for a magnitude 9 Cascadia Subduction Zone earthquake. What you notice is the red, orange, yellow, green. So what does that mean? So what does red mean? What does orange mean? What does yellow, green mean? Well, this is in the MMI scale. And so the MMI scale is defined qualitatively. So we have numbers 1 through 10 plus. Right? And it refers, this may be a little small for you to read, I'm sorry about that, but I'll read this. So for example, at the 10, at the extreme level, poorly built structures are destroyed. Just massive destruction. Water thrown out of rivers, lakes, or canals. Pipelines completely destroyed. Right? Well, let's look at something like where we are, so somewhere in the valley here. right? All along, so Portland and Corvallis over here, and all along there, what are we looking at? Kind of an orangish color or so, right? And then these oranger colors on the MMI scale are maybe 6 or 7, and that's light and moderate. So for example, for level 6, it's felt by all. People walk unsteadily, windows crack, dishes, glasses fall off shelves, pictures off the wall, and things like that. Right? So it's a qualitative description of what you would feel. It's not defined necessarily by an instrument. Right? Or I mean, the instrument is people. Right? People reporting what happened. But that's just an illustration of another type of scale, MMI scale. But let's take a look at these zones here. So this got right on the coast, between the coast and the valley, and then east of there. Right? So we can separate that out into 4 different zones, these shaking zones. So one would be the tsunami zone. So what are we talking about in the tsunami zone? This is really bright red. We look at our MMI scale like I just read, you're talking about really total destruction. Buildings are completely leveled by the shaking. Okay. How about in the coastal zone? So in other words, just outside of the tsunami zone, so still in this bright orange. Now we're looking at severe damage. The steering of cars affected, right? If you were driving, you actually would have a hard time keeping the car straight. Right? Extensive damage to masonry buildings and things like that. How about in the valley? Well, the valley was in the light and moderate, right? That's the other one. So we're looking at widespread moderate damage. And then last is the eastern zone, like over in Bend and east of the Cascades. And there it's relatively mild. We're looking at just like pictures getting knocked off walls and things like that. And so one important fact of that is that eastern zone is really the critical hub for the recovery. So one thing when we're looking at the impact that this has on the state is really need to look at what resources are on the eastern side. And a lot of the utility people in the room know this as well. We're really looking at what kind of resources are over there, and do I have enough resources over there, and can I get them to the coast? Right? So the eastern region is really important as a staging area for the recovery effort that will be needed in the western part of the state. Any questions or comments on anything so far?
So do you have a 10,000 years chart of Japan, like you did with Ori?
No. Like the frequency of earthquakes there?
Yeah, I mean, I was just curious if you had.
I don't. Does anyone know anything about that? So the question was about if there's a record of earthquakes for Japan, similar to that timeline that we had for the Pacific
I
Northwest.
think that Goldfinger has it because the orphan tsunami was part of the basis of the nailing down the Cascadia concept.
Okay. So I'll make a note. Let me follow up and see if I can get that information. If I can get that, I will put that in the repository. So when you talk about the magnitude of shaking, I'm just going to introduce this just a little bit, but one very important measure that we talk about is the peak ground acceleration. So if you actually measure, so if we had an earthquake right now and we had a seismometer that was measuring the ground movement, you'd have a time series, right? It would trace out a particular motion of the device over time. Well, somewhere in that time series, there's a moment that was the maximum acceleration that was seen. And that's what peak ground acceleration is, or PGA is peak ground acceleration. However, it's defined a couple different ways. I'm going to show you if we go to OHelp. So one resource I want to show you is the OHelp website. This was developed, sorry, it's a little bit, let me zoom in a little bit here. I'll just leave it out here. I'll put this up in a link to this as well, but if you just search for OHelp, spelled like it sounds, you'll find this. And this was done with Dogami and the Cascadia Lifelines program worked on this. But what you can do is you can look at a couple different scenarios here. For example, if I look at the Cascadia Subduction Zone, if I click on that, we can pick a magnitude 9. Actually, 9 through can go down to 8. And we can look at something like ground motion. So let me zoom into our area here. And if we want to see in a modified Mercalli scale, I can click on that, and then here it shows me, it colors this. Right? Remember, the modified Mercalli is the qualitative scale. And so here, it comes off the side of the screen, but you can see 3, 4, 5. Right? So this corresponds to a certain qualitative description of the shaking that was felt. Right? Or we can look at it in peak ground acceleration. There. And again, if I click here, I'll get a legend. And you can see, sorry if you can see that. But yeah, for example, 0 to 0.5, that's the green over here. 0.3 over here along the coast. Right. So I just want to show this resource that's out there. Again, I'll put a link to that in the course repository, or if you want to make a note, just search for it. OHelp. It has a number of other mapping functions as well. Shows you, like, if you look over here, you can find, for example, probability of exceedance of certain certain ground motion. So 20% probability of exceedance of a certain PGA in 50 years. Yeah. So for example, there's you have a much higher risk of exceedance of 0.3, 2% 50-year chance of 0.3 PGA along the coast. So, and they also have some information about where the landslide threats are. So that's over here. Landslide hazards as well, you can plot that. Right. So a number of very good resources there for Oregon, if you want them. Again, that's the OHELP website. But the one thing I want to talk about anyway is the PGA. When I look back at the PGA, so if I go to ground motion, peak ground acceleration, if I go back to that. Okay, so you look, oh, that's peak ground velocity. It's right there. Yeah, so PGAs, so I have like 0.3 PGA here, and going on to about 0.0 as they go there. So what does that mean? That's actually the bedrock peak ground acceleration. So that's the PGA that will act, that's the bedrock underneath the soil. The peak ground acceleration that the structure actually sees, that you might be interested in, your building or your substation or whatever, actually depends greatly on the type of soil that's built on. Right? So this really shows the underlying peak ground acceleration of the bedrock. But you need to know more. You need to have an engineer come and look at your site and know something about your soil to determine what the peak ground acceleration will be at the surface. And then the structure will also then determine what the peak ground acceleration is of it, right, of certain floors of the building or whatever. So there's a couple other steps that are necessary to go from the peak ground acceleration of the bedrock to understanding what your structure actually sees. But just so you know that when you see these PGA numbers in this, that's the bedrock PGA.
If you're doing like site-by-site analysis, do you need to do soil samples, or if you're doing like a system-level analysis, or the economy maps adequate information to understand, or is it just
you need to have someone understand what how the soil will respond, because you could have two sites that are in the same shaking zone that could have very different PGA responses. So what this gives you is the underlying PGA response that would serve as the input for that, but then someone that's a soils expert would have to tell you sort of what kind of response that you would expect at that site.
And existing soil maps are not granular enough or distinct enough to give you a ballpark understanding?
My understanding is no. From what I've talked to the other experts at OSU, that you really have to do it, because I asked the same question actually at one point. I was like, can we extrapolate this to some larger understanding of roughly the soils? And they said no, it can totally depend on the area that you're in. So, yeah, you have input?
At Oregon State, we worked with Tsunami because the inundation zone general model, was the basis for the Coast is Toast article. And that's a macro analysis. Dogami helped us do a micro analysis for actual locations on Camp Rylea, and you get into there's a velocity, I forget the name of it now, but an actual whole body of knowledge associated with what's going to happen, the subsidence, the energy flux density, and that kind of stuff. And Dogami is very helpful, particularly for investment decisions for things you haven't done yet. They would prefer that you ask them up front, as opposed to, after you've already capitalized the project, finding out that you're putting it in the wrong place. And then, as you point out, the geotechnical analysis is closely related to that. But Dogami is a great resource.
Yeah, great, thank you for that. Any other input on that? Anyone? No? I know some people in the room have done actual studies on their substations, soil studies.
We use Tsunami maps for the broad brush assessment, but then when we go to sites, we can be site specific. For example, we use the Tsunami map for liquefaction at one of our sites on the coast. We said it would liquefy, but when we did our site investigation, it said no, it will not. So the maps are good for a broad brush approach to see whether you think you have a problem, but you do have to go to get site data to finalize the answer.
Okay, so that's good. So you can get a broad brush answer, but you need to drill down deeper to understand what's going to happen.
It forced us
to literally drill down deeper. Yes.
I am Yume Wong. I'm with Ogami, so I can provide a couple of quick responses. The type of hazard maps that we make, earthquake hazard maps that we make, are regional, so they're not site specific. And in general, they are on the more conservative side. So what Leon just mentioned, the site that he looked at, our map showed that there was a liquefaction potential, and it's not surprising that after doing a site-specific study, it's actually not liquefiable. So in a general sense, I think this is answering your question a bit. If you look at Oregon, the valley, the Willamette Valley has more young sediments that are deposited through rivers, and the entire valley has softer sediments that are more prone to shake harder, and especially right along the rivers, they're more prone to liquefaction. If you take, again, a broad brush look and you look at the Coast Range and the Cascade Range, they're mountains, so it's not surprising that that's where you would expect to have earthquake-triggered landslides. So that's like on a very broad brush level.
Thank you. That's great.
I might add that I asked Yume about this particular site. She told me to Google it, so she was right.
Any other input, comments? Okay. So on the topic of liquefaction, here's a map as well of liquefaction and landslide threats along the coast. So both of these are showing the purple shows liquefaction threats, and the red shows landslide threats. So this brings up a point that I want to stress, that we'll talk about a couple different ways that shaking can cause soil to fail or a structure to fail. One obvious thing that people think about is it just shakes it apart, right? But that's only one way that the shaking can cause damage. Another is that you can trigger landslides. So land that looks stable but is in fact barely marginally stable, and then under the shaking it releases. And so you can have landslides that destroy roadways or structures. And then the other is liquefaction. And particularly liquefaction is a threat for our area. And so liquefaction is something like this, where you have soil that looks solid, that's holding a certain amount of water, but under the stress of shaking it's no longer able to hold the water. It comes out and it basically turns to basically like a wet sand. And rather dramatic example of things just sinking right into that. And so you can have structures, foundations that seem strong, but they are in fact not. And once the shaking starts, the structure will fail, or the foundation will fail underneath the structure. There's a little video of this that I showed in my class. It's kind of nice. It's not in English, so I'm not even going to play the audio. But it's a nice. But there are subtitles, which is nice. So it's an illustration of this guy. Or just watch it.
装进一些干的沙子，沙子要装多少呢？也不用太多，大概是刚好能够盖住这个水的表面就可以了。再一点点。OK 了，现在我们用肉眼从上往下看，当然只看到干干的沙子，我们不知道它里头还有多少的水分。但是从这个玻璃箱子的侧面，我们清楚地看到了，其实这一块土地里头蕴含了相当饱和的地下水。OK， 我们现在试着在这块土地上盖房子。假设我们住在这个地方，从此就安居乐业了吗？不要忘了，台湾位在地震带上，万一不幸发生了大地震的时候，地层会剧烈的晃动，晃动会产生什么现象呢？我们看到了，悲剧发生了，土壤瞬间异化，然后造成了地面的陷落。房屋的崩塌，淹在水中了，有没有看到？日本的3.11大地震，就是因为土壤异化，造成了相当严重的灾害。
Such a little illustration then of how you have something that looks solid, but it's not once it starts shaking. So, and liquefaction will come up again and again over the presentations. So that was the earthquakes. We're talking about the failure due to earthquake, peak ground accelerations due to the earthquake, but that's only part of it. The other part is the tsunami for the coastal region. So we got the earthquake and the tsunami. So you get both of them. Right? So what happens in the formation of the tsunami? As we mentioned, the Juan de Fuca plate diving under the North American plate. That's locked right there. So it's pushing, it's crushing the North American plate back. At some point that will pop, and that will cause a large wave that propagates in both directions. It'll propagate to the left and the right. So you have one wave that's sent out across the ocean, another set of waves that are set toward that are going toward the shore. Right? So what kind of damage or what kind of threat does this present? The tsunamis are basically they're waves with extremely long periods. So it's a wave, it's extremely stretched out, super long period to it. So what happens is when that comes into shore, right? Like if you think like a disaster movie, you think like a big curling wave that comes over and smashes down. But it's not like that. Instead, it's a wave that is so long that as it comes in, it just from a perspective of a person on the beach, it just like the ocean just comes up and just keeps coming and keeps coming and keeps coming. Right? So it acts like one massive moving plateau of water rather than like a big curling smashing wave. Right? It's like the ocean just comes up and decides it wants to come inland and just keeps coming relentlessly. A vast moving plateau of water. Right? The tsunamis travel super fast. Since they're such long period waves, they travel really, really fast, like around 500 miles an hour. So if you're actually out, you can actually, it may pass unnoticed under ships because the wavelength is so long. As they come closer to shore, they start to experience some of the friction, the bottom of the bathymetry at the bottom of the ocean. That causes the wave to bunch up a little bit. So as it gets closer to shore, it kind of bunches and comes up more. And so then you have this big column, this big massive plateau of water that comes and moves up into shore. Right? So the actual, that what you see on the coast may come up 30 or 40 feet and come inland. Another thing that happens is that when this fault happens, when this pops, this bunch of land jumps out toward the ocean. It also drops down. That's called subsidence. So that the North American plate's going to get pushed back. When it pops, it'll jump out and down. So that increases the amount of tsunami run-up. Because not only did you create the tsunami, but you went out and down. So now your elevation is a little lower than it was before. So that will increase the amount of run-up of the tsunami. How long does this take to happen? Something like 20 or 30 minutes after the earthquake before the tsunami arrives. So you can think for coastal communities, it's really, really a nightmare scenario. Or especially imagine something like this happening at 2 a.m., right, where you are now experienced to 5 minutes of severe shaking and just the trauma that would be. I mean, the structure's falling down around you, wondering, is your kids or whatever in the next room? Are they safe? What's going on? The trauma of that. Trying to deal with that, trying to deal with dragging people out of the wreckage, figuring out what you're going to do, and all the while the clock is ticking. 20 minutes from now, there's going to be a wall of watery death coming for you. Right? So it's really a double whammy for those communities to deal with both of those things right in quick succession. It's not just one wave, it's actually several waves. For example, in the Tohoku, there was as many as 5 waves that came in. So there's a series of them. Also in Chile, there were several waves as well, something like 3 to 4 of them. Okay. We have something like 70,000 people are in the tsunami inundation zone along the coast. There's a very large population that's under direct threat of that. The actual the ports and larger population centers, though, are further inland such that they're not under direct threat from the tsunami. Certainly from the earthquake, but not necessarily from the tsunami. So it's mostly the smaller coastal towns. A lot of the coastal towns aren't quite as large, but there's still a lot of people there. Here's a picture from an earthquake in Gulf of Alaska, magnitude 9 in the Gulf of Alaska in 1964. So this was a tsunami produced by that earthquake 1,300 miles away. And this is a picture of Cannon Beach in northern Oregon. And here's a house that was there, and now it's there. Here's a bit of bridge that's here, a bit of bridge that's here. Right? And that was a tsunami that was generated over 1,000 miles away, okay? and the damage that it did when it came in. Right? So very, you can imagine then what that experience would have been like only 100 miles away, not 1,000 miles away. Here in the Tohoku earthquake, here's measurements from wave gauges actually along the coast. So here's Port Orford, Charleston, Newport. Right? So what's shown here is a measurement of the actual water level. And this was in the Tohoku earthquake. This was 2011. So this was an earthquake generated off the coast of Japan. And for example, at Port Orford, you can't quite see the scale here, but at Port Orford, this is 4 feet right here. So they had almost 5 or 6 foot waves coming in, right? Enough to certainly push some boats around there. And that's from a tsunami that was generated all the way across the ocean. So it's just a tremendous, almost mind-boggling amount of energy that's released there.
Crescent City got, I know it's in California, they got a lot of damage to their harbor.
Yeah.
I was down there, I saw the pictures of it, I didn't realize, is there some reason, it seems like the amplitude it's caused more destruction down there. I think Crescent City got damaged from the Alaska one too. Is it just sticking out or is there something?
I don't know. I have a picture of that. I'm going to skip way ahead to the. No, I'll come back to it a little bit later. It's too far ahead. But I have a picture where we show the propagation of that tsunami. And so, yes, it totally verifies that it was stronger down here, but I'm not quite sure the bathymetrical reasons for that.
It's the bathymetry, Pete's Jordan Sky. There's a bathymetric pattern that focuses the energy right at that place. That's going to be used for other things, as well as planning for earthquakes. But if smacks Gold Beach and Port Orford and Crescent City, then you can plan on it.
Yeah, well, see in the tsunami map it shows that too. Yeah. Any other questions or comments? Okay. So the tsunami. Here's a picture of Japan, this particular neighborhood. This is just widespread destruction from the tsunami, just completely wiping things out. And what we point out here is just the neighborhoods, hospitals, police headquarters, all of this. You had all these very important facilities, all in the tsunami inundation zone. In the case of this Japanese community. We look at something like Seaside. This is north, so we're looking south. The ocean's over here. So north looking south towards Seaside. And all of this, all here, this is all right here. Again, now we flipped, now we're looking north, the ocean's over here. But all that area right here is all in the tsunami inundation zone, all that purple. All that purple means it's all going to be underwater. In fact, there's another researcher at OSU that does work on agent-based modeling. So what you do is, it's kind of like a fancy game. What you do is you drop agents, which are people or cars or whatever, but in this case it's people. So you seed this with a bunch of people and you program each of the agents to have a certain behavior. The certain behavior is to run from the tsunami. And then but there's only a certain number of bridges that go across here, and they have to try and get to certain safe points. And so what happens is then you seed this with a bunch of agents, then you send a tsunami their way and you try and see if they can all evacuate in time. Like, is there enough actual roads and means to handle that much flow of people for them to get out to certain safe points? And no, they don't all make it. Some people get caught. But anyway, so but these communities that are very, very threatened by that. So that's for Seaside. But what about the rest of the Oregon coast? So this is a plot here. Again, I apologize, it's a little bit small. But what's shown here is the percentage of developed land that's in the tsunami inundation zone. So the larger this bar, the more land for that particular community that's in this tsunami inundation zone. Here's Seaside, that's almost 90%. There's Gerhardt, that's almost 80%. Cannon Beach, Rockaway Beach. Waldport has a lot. Yachats, that's no surprise if you go through Yachats. Right, so shown here is that we gave the example of Seaside, but there's a lot of coastal communities that are in the inundation zone. A very, very significant amount of land and people living on land and structures in land that will be underwater in the tsunami. Then I talked about the subsidence. Just a little slide on this. What's shown here is the magnitude 9 amount of subsidence. So the subsidence is the amount of land that is how much the land drops. So I mentioned that we're pushing the North American plate back. When that pops, it'll pop out and drop. And how much does it drop? In some cases, almost upwards of 9-ish to 10-ish feet. Like off the coast and around the coast, you're looking at anywhere from between 3 and 7 feet or something like that. Right? That land actually drops from all that pent-up energy that it's had over the last 300 years of pop out and down. And then that will be lower. So that will also very much change the beaches and the bathymetry of that area when that happens. So I think that's everything I have for a quick rundown on the Cascadia Subduction Zone. Is there any questions or comments on that? So what kind of, yes, go ahead.
Yeah, so I saw a presentation on this by the University of Washington up in Seattle, and what they noted was the subduction zone will actually trigger additional earthquakes that have different personalities than the subduction quake. And so when you hit the ground acceleration, does that factor in the potential that you have other faults triggering?
No. There's one slide here. I'll talk about some of the other faults that are in this area. We're going to focus largely on the Cascadia Subduction Zone. Yeah, but you're right. It's going to trigger a whole bunch of other seismic activity. And I don't have an expert analysis of what that is. I don't know. Has anyone look at what other earthquakes are going to happen after the Cascadia Subduction Zone?
I think the big assumption is that any active any active fault, crustal fault, that's not the subduction zone, could possibly be activated. And it might not, activate right away, but it could accelerate the span of it. So, for instance, the Portland Hills Fault, which creates the Portland Hills, could get pushed to activate, within months or years afterwards, sooner than it otherwise would have, because there's changes in the stress regime.
So what are some of the anticipated impacts of this Cascadia Subduction Zone? Again, this is largely from that Oregon Resilience Plan report. Very large-scale damage to many, many lifelines. Okay. So when we talk about a lifeline, remember I talked about the Cascadia Lifelines program clip? What is a lifeline? A lifeline is a certain system, societal system that's important to us, right? So it's things like water and power and transportation, things like that. Most of those lifelines are spread wide. They cover large amounts of area. And so you're looking there, obviously those are very vulnerable. So damage to many, many lifelines. Fatalities are estimated to be anywhere from 1,000 to 10,000, something like that, from both the earthquake and the tsunami. Tens of thousands of buildings destroyed, tens of billions of dollars in economic loss, tens of thousands of displaced households, people that will need refuge or boarding afterward. Total damage in the tens to hundreds of billions of dollars. Another interesting thing is that millions of tons of debris. So when you show some of the pictures of the destruction, particularly for Japan, what you'll notice is just debris everywhere, stuff and junk all over the place, right? And so that's a huge task, just managing that, getting that out of the way so that you can get in and do what you need to do, and then managing all of that debris. That brings me to a couple key points. When we talk about the impacts of these things, is that stuff will break, the broken stuff disrupts things, and then people move away. That's what we see in the communities that are badly affected by disasters, right? Is that we tend to focus on stuff being broken, that's the most immediate thing, but there's a whole, it sets in motion a whole set of things that affect the long-term viability of that community. So that's the direct and indirect causes. So the direct cost is the stuff breaking, right? Buildings shaking apart. But then there's a very large amount of indirect costs, and that's the fact that you're changing the economic trajectory of that community. If you cannot keep people in place, they will leave and they won't come back. And that's what you see, for example, for Katrina and things like that. I'll show you another example. Kobe, in 1995, Japan earthquake in Kobe, right? Permanently changed the economic trajectory of that community, right? It's not like you just recover and you come back. If the trauma is big enough, people will leave, businesses will leave, they won't come back. And then that community is different from now on. So that's this direct and indirect cost. And the indirect costs are likely much larger than the direct cost, meaning the cost of changing the economic trajectory of that community is likely much larger than the direct damage from the earthquake. So when we talk about recovery, what kind of recovery timelines are we looking at? Again, this is from this report, but I should mention that talking with a lot of people, that there's a wide range of opinions on these numbers. So you certainly may disagree, or I've certainly seen people that think this is maybe a little bit rosy. But anyway, so some general, I'll just show you these numbers that were in the report. So you're looking at things that are like months. For example, electricity in the valley, where the shaking is moderate, 1 to 3 months, but along the coast where the destruction is much larger, something like 3 to 6 months for recovery of that. You may have a different opinion. But other services, what I kind of want to stress here is you're looking at recovery periods, all these estimates, they're not in days and weeks, they're in months and years. Yeah. So that's one thing to focus on, is that, and I want to stress this, when we talk about Chile, when we talk about Japan, and a little bit later we'll show a particular metric, when you look at the recoveries for those communities, for the seismically prepared countries, like Japan and Chile, their recovery times are measured in the days or weeks. But we're really looking at months or years as our current estimate. So if we want to join that club of countries that are ready for this, or at least as ready as they can be, we really should be looking at stuff that's in the days or weeks. Those are the kinds of timelines that you're looking at, and not months and years. Okay. So for example, in Chile, in 2010, the Maule earthquake was almost a magnitude 9, and 90% of communication services and 95% of their electricity within 2 weeks. And all their airports and stuff, commercial flights restarted 10 days later. Okay. In Tohoku, the 2011 Great East Japanese earthquake, 90% in 10 days, and 90% of communication in 2 weeks, and cell back in 20 days. So again, these are kind of benchmarks that we can look at and we could say, well, could we do something like this? This is what a country that has its crap together in terms of seismic preparedness, this is what they can do. You know, could we be at a point where we could hang with that and have those kinds of recovery times? Look at some other infrastructure that we impacted. Bridges. Majority of bridges along I-5 were built before modern seismic standards, so they're at risk. Something like 19 of those bridges estimated to have heavy damage. Several of them likely to collapse. On Highway 101, of the 135 bridges, 56 of them may be collapsed. Another 40 of them may be largely damaged. So the bridges are very vulnerable. They're built before modern seismic standards. And if the bridges themselves aren't destroyed, there's a tremendous risk of landslides along I-5 and Highway 101. So you're also going to have landslides that are going to cover those roads and damage them. So I-5 and 101 are greatly threatened by the earthquake from a couple different mechanisms. They're not really ready for that. Okay, another one, and you may is certainly the expert to talk with on this, but a critical energy infrastructure hub here in Portland, right along the Willamette River. And that's a liquid fuel hub for this area. Almost all of our liquid fuels are processed here, shipped in and out, processed and held in tanks. There's something like a couple days of supply there only, right? So we have, and all of this is built on highly liquefiable soil. So this is a tremendous threat. So we have a bottleneck, a huge amount of liquid fuel for the whole area that comes through this one region that A, doesn't hardly have any storage capability, and B, even if it did, it'd probably be destroyed anyway. Yeah. So that's a very, very significant threat to the area. And you may, I think you talk a little bit more about that? Yeah. So hear more about that. But that's a very significant threat. The power system, we'll talk a little bit more about that, particularly Leon, but that's also certainly a lot of threats there in terms of our electricity. The building codes were not really updated for Cascadia Subduction Zone event until 1993. So you can think of structures before 1993. And for the most part, they were not built with the large earthquake in mind. So a very, very significant amount of the infrastructure is not prepared for that. Like half of public schools could collapse. How crazy is that? Huge, huge amount of structures that are not ready. We mentioned the bridges. And for power systems, mentioned it's really one of three things that are necessary for businesses. So I'll come back to businesses here in a second. But for a business to stay in place, right, it really needs, the workers need to get to it, the building needs to be safe, and it needs to have electricity. Those are really the three most important things. So power is one of those three most important things to keep the business in place, and keeping the business in place is one of the most important things for keeping the economic trajectory of that community similar to what it was before and not losing it forever. Okay? So power is super important for that. And as we mentioned, there's going to be severe road damage though, from landslides or bridge failures, so it's going to be really challenging to get out there and fix that stuff. Okay. The businesses that I talked about, businesses can suffer something like 2 to 4 weeks without services. At that point, they're going to say, screw it, and move away. They're just going to leave it, write it off, lose it, go do something else. Okay? So obviously that varies a little bit on the business and things like that. But that's sort of that's anyway roughly the kind of timeline that you're looking at to try and get that service back if you want to keep that economic resource in place. If you push much beyond that, you're risking that you lose that. The community will lose that. Okay? And as I mentioned, the building has to be safe, and the workers have to be able to get to it, and the electricity has to be working. And I mentioned that the trajectory of the economy can be changed. Another important thing is the direct and indirect damage, right? You have the direct damage to the building, so it doesn't work anymore, the business isn't there, but then you have the indirect damage of the fact that that business is not functional. Right? Those consumers are not coming and spending their money there. The workers are not getting paid for working there. The people that own the business are not getting paid for the business. Right? There's a huge indirect impact that happens after the fact. So that brings the last thing, and that is how would we define resilience? So we've kind of introduced all the concepts. There's a bunch of different definitions for it. The one that I like best is the one that's shown there, is prepare, absorb, recover, okay? Which is PAR, P-A-R. Right? So if you want to remember, you could say like resilience is par for the course or something like that. Right? But PAR, prepare, absorb, recover. That means if you wanted to improve the resilience of a system, you could focus on any three of those things. You could prepare it. So before the event, you could have it well prepared. That would improve its resilience. Okay? You could make it so that the structure, for example, can take shaking. You could upgrade it so it's seismically ready, right? Or you could move it to another location so it's out of the tsunami inundation zone, right? Or you could prepare the soil so it's not so liquefiable, right? You could do those things. You can make it so that it can take the shock and keep working. Okay? Another thing that you can do is you can make it so that it can recover quickly. So you can say, okay, fine, maybe that'll get knocked out, but I have a bunch of spares ready. I have a backup plan that's ready so that if it gets knocked out, I can come in and I can fix it relatively quickly. Okay, that's the recover part of it, right? So that would also improve its resilience. So any three of those efforts can improve the resilience of a structure. It's really the past, present, and future, right? Prepare it, absorb when it happens, and recover after it happens. Okay? So that's, I think, for me anyway, that was the most helpful definition of something that's resilient. It's something that's prepared, something that can absorb, and something that can recover. The Kobe earthquake, I mentioned this, magnitude 6.9 in 1995. A lot of damage to this in Japan. But it's interesting here, they have some actual numbers on the economic recovery. So mining and manufacturing activity, only 80% of what it was pre-earthquake. Shoe production is 60% of what it was before. So it's a very large shipping point there, and they did a lot, very large shipping port. They did a lot of shoes. Sake breweries, that's very sad. Less than 50% of their pre-earthquake levels. Okay? But you see anyway that this stuff didn't recover all the way. So if we translate that to what that would be for Oregon. So in 2010, the output per person in Kobe was 13% lower than it would have been without the earthquake. So they have a permanent 13% depression of their economy, right? If we translated that to Oregon, if Oregon were to experience a 13% decline in output per capita, output would fall by over $6,000 per person. And Oregon's output per capita would fall from 9th to 23rd among states. So you're talking, again, just stressing the fact that it's easy for us to think, oh, this earthquake's going to come and it's going to cause all this damage. But the effects are much longer than that, right? You're really taking yourselves down a couple pegs in terms of your economic output. Okay. Transportation system, you mentioned I-5. I-5 is obviously the critical corridor. And we mentioned the bridges. There's many, many bridges that are vulnerable, and also the landslides. There's 49 known landslides along I-5 that may become active during the earthquake, right? That may destroy that. So the bridges and landslides are a big threat to I-5. Also mentioned here that the rail lines are not well studied. So we don't really know a ton about how well the rail system will do. Obviously, it's going to be similar situations. Rail lines, particularly is coming into Seattle and coming into Portland, run through a lot of hilly areas. So I imagine a lot of those tracks will be threatened by landslides as well. But it's not something that's extremely well studied. What about airports? Most of the large airports are not in the severe shaking zone. And so for the most part, it's thought that they'll probably do relatively well. But they're going to get messed up by the disruption of jet fuel that comes through the critical energy infrastructure. So the airport may be okay, but they may not have fuel for it. How about ports and shipping? Most of the large ports are not in the most severe shaking, and they're not in the tsunami inundation zone, so that's good. However, there's a chance that you could trigger underwater landslides that actually make these passageways unpassable by large vessels. So again, not super well understood, but there are some risks there as well. How about communication systems? Here's just a picture from earthquake in California, cable rack destroyed. Here's in Peru, here's a cell tower got knocked off a building. Right? Obviously, these systems are vulnerable too. I'm not going to talk a ton about that, but these communication systems are highly dependent on other resources, obviously electricity and things like that. And it's presently expected there'll be very large failures of the communication system. So that's also very vulnerable. How about water and wastewater? Here's the Kobe earthquake. Here's pipes running to a tank, and you can see the pipes just completely sheared and broken off. Short answer is that water systems are also very vulnerable. Here's a picture of in Haiti, after the earthquake in Haiti, here's a water treatment, an impromptu water treatment plant that's set up. So it's interesting just to ask questions, do we have this kind of capability? Could we do this for communities? Right? How water systems fail, they're actually vulnerable to a lot of different forms of the shaking. One is the liquefaction. So the tanks, for example, in the critical energy infrastructure area, you have tanks that are built on liquefiable soil. So they're going to shift and they're going to be damaged there. They can be damaged by landslides. Lateral spreading refers to the fact that the land just moves. So that's like I had a tank here and I had a tank here, and they're connected by rigid pipes, but now these tanks moved, right? So those rigid pipes are going to shear and break. They're vulnerable to that. The shaking themselves actually can cause waves inside tanks and type of water plants, and cause stress on the walls of the tank and walls of the structure. Damage from those, and then if the water treatment facility is on the coast and it's actually in the tsunami inundation zone, then it can get damage from the tsunami as well. So water system is very vulnerable to many, many forms of damage. Just as a summary of that, another interesting thing to point out is the storm sewers. So we're looking at failure of storm sewers and wastewater treatment. So sewage will overflow. Sewers will plug within the first few weeks. What will happen is people will try and flush their toilets by dumping buckets of water down. But that doesn't, it's not enough. What happens, it works for a little while, but it doesn't keep working, and eventually that system plugs up. And you can imagine, I mean, you're dealing with all this other crap, well, now literally, right? Now you got to deal with the community that's got wastewater problems, right? So that's going to be widespread. And then that's going to overflow and pollute other bodies of water. So the fact that your sewer system's not working, going to overflow and you're going to pollute other things. An interesting thing is this chemical toilets. I just made a note of it. It's on this is page 222 of this Oregon Resilience Plan document. Again, you'll get the slides after the fact if you want to look at them. But that's an interesting thing. So for example, I have a guide from the Benton County Sheriff's Office in Corvallis. It's a very good guide. But they, like many preparedness guides, they don't talk much about the waste issue. But it's very overlooked. So there's a lot of guidelines, for example, in terms of, you should probably have this much water, you should have this much food, you should prepare to shelter in place for this amount of time, do you have some camping gear, things like that. Say, yeah, but what do you do about the waste? Right? There's no guide for how you make a latrine or anything like that. An interesting point that's brought up, though, is the use of these chemical toilets. And so if you go and look, there are guidelines for how you can take 2 buckets and use them to make chemical toilets for actually, that you can use as a latrine for some length of time. So I just bring that up. That's sort of a underappreciated fact of resilience, that you got to deal with that. And so, if we're in positions where we're looking at improving the resilience of our communities or our workforce or whatever, that's dealing with the waste is a non-trivial issue. One other thing I'll point out is that you also lose water for fire suppression if you've lost your water treatment facilities. So that's another big risk, is having fires in the days and weeks after the earthquake and not being able to properly address them. So is there something that we can do? Are there early warning systems that could help us with this? I have a very, very short slide on this. It's actually a totally fascinating topic, but I'll just mention a little bit about it. We are working on one called the Shake Alert System. And it's a project of the U.S. Geological Survey and projects in largely the state of California and California universities. There's an early version of it, 1.2, just rolled out this spring. It's still in the early phases. And the plan is to do something like an Amber Alert type model, where, you guys are familiar with Amber Alert, right? If there's like a abducted kid or something like that, you get a message on your phone. Similar kind of thing. So you would get a message to televisions or radios or your phone or whatever that says, hey, there's possibly an earthquake that's going to happen. How does this work? Okay. When the fault slips, there's 2 types of waves that are generated, a P wave and an S wave. The P wave is a pressure wave. It's actually sound. It's a sound wave in the earth. Right? It's actually a change in density that propagates. It's a pressure wave. That is not very damaging, and it travels faster than the S wave, which is the seismic wave. The seismic wave is the larger ground motion and shaking. So when the fault slips, there's a ping that goes out, if you want to think of that. That ping travels faster than the ground undulation and the ground shaking. So if you can hear that ping, right, then you know that the shaking is coming soon after that. That's the way that these early alert systems work, is they listen for that P wave, the ping, ahead of the S wave. So how much time do you get? Depends on how far away you are from the earthquake. If you're right on top of the earthquake, you might get 0 time. Okay? The pressure wave and the shaking wave will occur at the same time. However, if you're some tens of miles away, you might get a warning time of some seconds to minutes, maybe up to a minute or something like that. Right? I'll show a plot of this. Here's what's shown here is distance from the earthquake epicenter. So this is 60 miles, 80 miles, 100 miles, 160 miles, and this is the warning time that you get. Okay? So 160 miles away, you're looking at just over a minute difference between the arrival of the P wave and the arrival of the S wave. Right? Hearing the ping and then actually feeling the shaking. What's shown here is a plot of the seismometers and detectors. This is in Japan. You can see the instrumentation that they have for seismic detectors. And this is a picture just for California. And you can see here that it's much less. So Japan is highly, highly instrumented. For us, it's still a work in progress, getting these instruments in place to really enable this kind of early alert system. A little more detail on the Japanese system is on that previous plot. There's about 4,000 seismometers there that detect that early pressure wave, that ping. Once they detect that, they send a message to TV. So you see a banner across the TV station that will say, earthquake warning. Also alerts sent to phones. Also sent across the radio. Apparently, this was new to me, but apparently you can have an FM radio that can kind of be woken up by a signal. So I guess it's more common in Japan. But anyway, they have radios that can be woken up that will say, oh, earthquake coming. It was online and active in Tohoku and was considered to be effective. They think it probably saved a lot of lives. I didn't see a specific estimate on the number, but it did alert people along the coast that there was a large earthquake coming. And as I mentioned then, if you're on top of it, it may not be worth much. But if you're tens or hundreds of miles away, you may get some warning time. So then the question, I think very fascinating question, particularly as a researcher, is what could you do with that information? Right? If you had 30 seconds of knowledge that large earthquake was going to happen, what could you do? What could you do for your system? What could you do for a power system? Right? What could you do if you were in charge of a water plant? What could you do with that information?
So we're at eWeb, we're putting in 2 of these with U of O. We're going to open, on one, we're going to open the spill gate to the canal, start emptying the canal. And then on the other one, earthen dam, going to open the spill gate, start emptying the
So you're going to spill dams when that happens.
spill the water.
Shut down hydro units.
One thing that we're looking at, Eduardo and I are looking at for energy systems research, is if there's something you can do, you can shut down the electrical grid in a certain way or island it in a certain way that would enable, even if it doesn't enable you to survive the earthquake, would allow you to black start quicker than you could otherwise. Right? So there's a lot of really interesting things. So that's cool that you're actually doing something with that.
Unless Trump comes out.
Yeah, switching to a backup control center, that's a great idea.
Another thought is to do automatic load shedding, so you're kind of initially staging for afterwards.
Yeah.
With that islanding situation.
Right.
60 seconds is a long time, a lot of electrical time frames.
Yeah. Not Cascadia Subduction Zone stuff. So just a couple slides on this, but to add the excellent question about, well, what other threats are there? Here's a map of a whole bunch of different faults from the Pacific Northwest Seismic Network. I have a very good website for this also. But just to plot, you can see that there's many faults all over the place. Mostly crust. So this is the subduction zone. That's the big one, right? And these are smaller crustal faults. But just because they're smaller doesn't mean that we shouldn't worry about them. For example, the one obvious one that was brought up was the Portland Hills. So there's the Portland Hills fault and the Oatfield fault that run right through downtown Portland. And actually, although this event is of much less consequence for the entire Pacific Northwest region, for Portland, for example, it could generate peak ground accelerations that are actually larger than the Cascadia Subduction Zone, right, in this area. And this is, I got this information from this excellent report that UMA is on. I'll put this up in the course repository, so please take a look at that when you're done. But just kind of dramatically, here's Portland, and then here's these faults shown on top of here, right? So you see, obviously, that's a concern for this area as well.
That was our office.
All right. So it's just stressing that obviously we're focusing here on the big one, on the Cascadia Subduction Zone, but for your particular region, there may be other faults that are of great interest to you as well.